Okay, so I'm going to share my screen now. This is our third lecture. This is our third lecture on CHM 121. And today we'll be talking about Henry's Law and Raoult's Law. Henry's Law and Raoult's Law. Remember that we started with solutions and solubility. And we talked about the solubility of gas in liquid. Now we should recall that the solubility of a solid and liquid is not affected by pressure. The solubility of solid and liquid is not affected by pressure. However, the solubility of a gas in any solvent is affected by pressure. And we understand from Henry's law that the solubility of gas increases in direct proportion to its pressure over the solution. The solubility of gas increases in direct proportion. Okay, so let me take this to slideshow. Okay, so the solubility of gas increases in direct proportion to its pressure over the solution. And the relationship between pressure and the solubility of a gas is expressed by Henry's law. If you remember Henry's law equation, please type it in the chat box. We talked about it on Wednesday, the relationship showing the relationship between pressure and the solubility of gas. That's Henry's law. Type it in the chat box quickly. Fantastic. Thank you, David. So we say C is equal to Kp, where C is the solubility of the gas, K is the Henry's law constant, and P is the partial pressure of that gas. So Henry's law, the solubility of a gas in a liquid is directly proportional to the partial pressure of that gas over the solution. Thank you, Simisola. Is directly proportional to the partial pressure of that gas over the solution at constant temperature. So we have the relationship again here, where you have the C gas, which is the solubility of the gas, equals KH and P subscript G, where KH is equal to Henry's law constant and PG is the partial pressure of the gas. From this equation, can you type the unit for Henry's law constant in the chat box quickly? So your C is in molarity, which is mole per liter, or you say mole per dm³, and your pressure is in atmosphere. What will be the unit of Henry's constant? In the chat box quickly, what will be the unit of Henry's constant if C is mole per liter and pressure is in atmosphere? Thanks, Tai. Tai says mole per liter per atmosphere, right? Do we have any other person? Ademuyiwa, thank you. Okay, Tai, well done. So you changed it to M per atmosphere. Okay. Oh, fantastic. No, David. No, David, that's not right. Mole times liter per atmosphere, no. Semisola, well done. David, please check your unit again. Doesn't seem right. It's not right. Kolawole, well done. Because you have to be careful with your units. It's very important. David, I'm waiting for the correct one. Okay, fantastic. That's better. All right, so the unit of K is mole per dm cube per atmosphere. So you can either write it as capital letter M per atmosphere, or you write your mole per liter, put it in brackets, divided by atmosphere. When the partial pressure of the solute above a solution drops, the solubility of the gas in the solution drops as well to maintain the equilibrium. So this can be used to calculate the molar solubility of the gas. So you can use Henry's law to actually calculate the molar solubility of the gas. So you have a solution like your carbonated water, you want to calculate the the molar concentration of the gas in that solution. In this case, we're talking about CO2 gas in the carbonated water. You can use this Henry's law to calculate the molar solubility of CO2 in your carbonated water. Now, the solubility of a gas in a liquid depends primarily on 4 factors. The first one is your temperature. The second one is the partial pressure of the gas over the liquid. The third one is the nature of the solvent, and then the fourth one is the nature of the gas. Now, like we said in the last class, one of the most common example of your Henry's law in real life is your carbonated beverage. Every one of you here, you're familiar with your carbonated drinks. You have the Pepsi, you have the Coca-Cola, you have the, I think this new one, Hearty Cola, you have all sorts of carbonated beverages. So they are all example of Henry's law in everyday life. You remember when you uncork, when you open your bottle of Coca-Cola, for instance, or you try to open the can, sometimes you hear that sound, shh, so you have your carbon dioxide escaping from the solution. Now your solution is a Coca-Cola, remember? Your solution is a Coca-Cola. So once you uncork, once you remove the cork of your Coca-Cola, some carbon dioxide escapes. What did you do? I want to ask a question now. When you uncork your Coca-Cola bottle, are you reducing the partial pressure of the gas or increasing the partial pressure of the gas? Quickly in the chat box. When you uncork your carbonated drink, are you reducing the pressure or you are increasing the partial pressure of the gas? If it's increasing, just type increasing. If it is decreasing, type decreasing. So Tai say you are increasing the partial pressure of the gas. David says decreasing. Simisola says decreasing. Francis decreasing. Okay. Bankole decreasing. Damilola. So I think decreasing. We have more of the decreasing. Fantastic. Tai, do you want to change your choice? Oshiba just says decreasing. Tomininu decreasing. Tai, do you want to change your choice? So they're actually right. When you uncork your Coca-Cola bottle, you are decreasing the partial pressure of the gas. This is a very important concept that you need to get. When you cork the bottle, you have increased the partial, you have the partial pressure of the gas at a relatively high value. So you have more of the dissolved carbon dioxide in the drink, and carbon dioxide gives you that satisfaction when you take your carbonated drink. But the moment you open it, the moment you uncork your bottle, please, Mosuro, please mute yourself. Mosuro, please mute yourself. Thank you. Okay, thank you. All right, so once you uncork, you are increasing the partial pressure. So what you're doing is you are giving the gas more space. So in the case of the Coca-Cola bottle, the CO2 escapes. So at some point, the solubility of the gas also tries to adjust in order to accommodate, to reach an equilibrium. So at that point, you find out that your drink is flat and you no longer get that satisfaction you get from carbonated drink. So let's quickly read what we have here. The most common solvent is water. Carbonated beverages are an example of Henry's law in everyday life. The dissolved carbon dioxide stays in solution in a closed pop bottle or can where the partial pressure of carbon dioxide was set at a high value during bottling. When the can or bottle is opened, the partial pressure of CO2 is much lower and the dissolved carbon dioxide will gradually escape from the pop. When the new low partial pressure equilibrium is established, the soda will be flat. This loss of dissolved carbon dioxide will happen faster for warm soda than for cold. And if you remember from our last example, I think it's one of the examples we solved where we asked that why will a bottle of carbonated drink suddenly burst open when you keep it under hot sun? This is the reason. So you have the temperature. When the temperature increases, the dissolved gas reduces. So more of the dissolved gas in the solution reduces, causing a lot of pressure in the bottle, and then the pressure causes the bottle to break. Okay, so we move on. Now, the concentration of dissolved gas depends on the partial pressure of the gas. The partial pressure controls the number of gas molecule collisions with the surface of the solution. If the partial pressure is doubled, the number of collisions with the surface will double. The increased number of collisions produce more dissolved gas. So this, what we're trying to say is when you have more collisions between the gas molecules and the solvent molecules, you're going to have more of the gas dissolved in the solvent. The illustration below shows that if the pressure is doubled, then the concentration of dissolved gas will double. Now let's look at this diagram. In the first image, you have the piston much at a higher level. So in this place, the partial pressure of the gas is really low. So you can see the gas molecule represented by the pink. Okay, let me put on my pointer here. You can see the gas molecule represented by the pink dots. So all those pink dots represent the gas molecule. When this piston is a bit higher, when you raise the piston in the bucket or bowl or what have you, you have more of the gas molecule occupying the open space. But the moment you press down the piston, what you're doing is you're reducing the space in this vessel. So you have more collision between the gas molecules and invariably within the solvent. So here you can practically count just about 2 of the pink particles in the solution. But when you reduce the piston, in this case, what you're doing is you're forcing down the space. So there isn't much space for expansion of the gas. So you're reducing the amount of space the gas molecules have to occupy in the container, thereby forcing it into the solution. So what you have is more collision between the solvent molecules, which is represented by the smaller blue dot, and the gas molecule. So here you can practically count the number of pink molecules here, which represent the gas molecules. So you have it increasing from 2 in this vessel to 4 in this vessel. You know, that's hypothetical anyway. So you can see that there is an increase between the collision between the solvent molecule and the gas molecule. In this case, you have doubled the pressure. So this is one thing you have to understand. When you increase partial pressure, when you increase the partial pressure and when you have lower partial pressure, You just need to understand it. Because if you don't understand the relationship, it becomes very difficult for you to know where you have more dissolved gases. So in this case, you have low pressure equilibrium, that's the low partial pressure of the gas, and thereby low concentration of the gas molecule in the solution. Meanwhile, in the second vessel, you have double the pressure by pressing down the piston. You have doubled the pressure and therefore double the concentration of the dissolved gas in the solution. Now let's apply Henry's law in calculation. The solubility of N2 gas in water. So here we're going to look at the solubility of N2 gas in water. The solubility of N2 gas in water, that's nitrogen gas in water at 25 degrees Celsius and 0.78 atmosphere pressure, is 5.3 times 10 raised to power minus 4 mole per dm cube. Calculate the solubility when the pressure is doubled. So in this case, we're going to apply your Henry's law constant for nitrogen. So the Henry's law constant for nitrogen is given by C is equal to Kpg. Remember your Henry's law, concentration is equal to pressure times the Henry's constant. So from here, you're going to calculate your Henry's law constant. So that's the first thing you want to calculate. Once you get your Henry's law constant, as the name implies, it is a constant, so it's constant. You can then use this constant for when the pressure is doubled. And you can see that in the example. So here we calculated the KH for the nitrogen gas, and this is 5.3 because when you make your KH the subject of formula, it becomes solubility divided by pressure. So there you have solubility divided by the pressure, and what you get is your 6.8 times 10 raised to power minus 4 mole per liter atmosphere. Thus, if the partial pressure is doubled, Henry's law predicts that the solubility in water at 25 degrees Celsius will also double to 1.06 times 10 raised to power minus 3 mole per dm cube. I do hope you did the calculation in your notes too. So the next example, even though the solution has been given, I want you to try it on your own and see if you're going to get the same answer with what you have on the slide. Do we have a deal? Type yes if we have a deal in the chat box. Do we have a deal? Okay, fantastic. All right, so this is the second example. The solubility of nitrogen gas at 25 degrees Celsius and 1 atmosphere is 6.8 times 10 raised to power minus 4. So please take all your constant out because I'm going to take it out of your face. So take all the units, all the values you need out of this question because I'm taking it out of your face shortly. So the solubility of nitrogen gas at 25 degrees Celsius and 1 atmosphere is 6.8 times 10 raised to power minus 4 mole per liter. What is the concentration of nitrogen dissolved in water under atmospheric conditions? The partial pressure of nitrogen gas in the atmosphere is 0.78 atmosphere. Okay, so I want your answer in the chat box. Okay, so what do we have? Okay, 5.3 times 10 raised to power minus. I have just two responses, right? Can we have more? David, thank you. Oreolua, I can see your solution. Okay, so I'm moving out your classwork because I have a classwork here and I have the solution already. So I'm trying to get this out of your face and move it to the next slide. So I don't have to, okay. So what do we have, guys? 5.3 times 10 raised to the power minus 4. All right. Okay, so when you look at this question, you again use your Henry's laws relationship. Solubility is equal. Thank you, Bankole. I can see your solution. Yeah, so C is equal to Kp, and the concentration at 1 atmosphere was given to be 6.8 times 10 raised to power minus 4 molar. So from there, you make your K the subject of formula, and K is 6.8 times 10 raised to power minus 4. Now, when K is 6.8 times 10 raised to power minus 4, you use this constant for calculating the solubility at 0.78 atmosphere. And if you do that correctly, you're going to get 5.3 times 10 raised to power minus 4. I want you to notice that when you have your pressure decreasing, your solubility is also decreasing. Your solubility is also decreasing. Now let's look at this classwork and solve this quickly. So this is a little bit more technical, just a little bit than our previous example, but I trust that you'll be able to handle this. So determine the quantity of carbon dioxide dissolved in 1 liter bottle of carbonated water if the pressure of 2.5 atmosphere is applied in the bottling process at 25 degrees Celsius. Given that Henry's law constant of carbon dioxide in water is 29.76 mole per liter per atmosphere at 25 degrees Celsius. I'm tempted to say that I'll give the first person who answered this question recharge card. And I think I'm going to give whoever answered this question first the recharge card. So who is going to be the fastest finger?
Fastest finger, no. You're never.
Hey, please mute yourself, please.
Are you sure that you muted yourself?
Mute yourself. Okay, so I think I successfully mute. All right. No. Taye, I can see 12 point no. 3.5 to no. You have to include your units. You have to include, someone says 0.08 mole. I want it in grammage. So grams or kilo. Grams or kilograms. Or what other grammage do you have? Yes, I want it in grams or kilograms. Ha. 71, really? 3.55. Really? Could it be that we're wrong from this side? 12.4. Units, please. 3.52 grams. Okay. 12.4 grams. Really? 3.5 grams, really? Oh, could that be true? Now I'm scared. 4.0 grams. Are you sure you're calculating this stuff? In 1 liter bottle of carbonated water. So your volume is 1 liter. You want to calculate, oh, okay, so I think the first thing you want to calculate is what? Your concentration, your solubility. Okay, so let's do it this way. When you calculated your solubility, what did you have? Solubility. So your C is what? Your C. So those of you that have typed your answers, please, units. So I know what you are talking. Okay, 0.0806. Ademosu says 0.0806 mole per dm cube. Okay, do we have any other differing answer? 71.4 molar. That's Gloria. No, that's yeah, that's Gloria. And David says, okay, I'm not going to take David's own. No unit. Okay, Alizi 0.0806. Okay. Okay, so I think I have more of the 0.0806 and 71.4. Interesting. So from that molar concentration, you're supposed to tell us the number of, so what's the number of moles now from your molar concentration? What is the number of moles? Now, I have two answers, 71.4 and 0.0806. Now, okay, we are done with molar concentration. From that molar concentration, what's the number of moles of CO2 gas in 1 liter of the carbonated water? So now your volume is 1 liter. Your molar concentration is either 71.4 or 0.0806. What is the number of moles? Ernest, David, Ajuwon, you all 3.52. No, I mean number of moles. What's the number of moles? Kolawale, I'm asking for the number of moles now. So I have two answers. Some says their molar concentration is 0.0806 and others said 71.4. David, okay, so from these two molar concentration, what's the number of moles? David, it can't be one. Okay, 1 mole, that's 44 grams. Okay, I think that's where the challenge is. Okay, so what's the number of moles? Exactly. So Ademosu says 0.0806 mole in 1 liter. I think that's fantastic. So if your molar concentration is 0.0806 mole per dm cube, and you're looking, or mole per liter, and you're looking at 1 liter of carbonated water, it means your number of moles in that 1 liter bottle is 0.806. Ademosu, well done. Do we have any other contribution? Okay, so while we wait for other contributions, Ademosu, from your number of moles, can you then calculate the mass? From this number of moles that you have got in 1 liter, can you then calculate the mass of the carbon dioxide dissolved in 1 liter of the carbonated water? I'm waiting for your response. I think, I don't know, depending on what the answer is. Joseph, no, we are not on Grammy. Joseph, we are not. Joseph, I don't know where you are coming from. We just asked about mole, and the only person that has answered is Ademosu. And Ademosu, move on to mass. So what's the mass? What's the mass in 0.0806 mole? So those of you who sent your molar concentration to be 0.0806 mole per dm cube and 71.4 mole per dm cube, I want to know your number of moles in 1 liter. Ademosu, you said 3.56, right? How? Okay, so mass in, let me bring this up. You're saying, Adimo, you said mass in 0.0806 is 3.55 mole. Really? Adebayo David, okay, Adebayo David, 3.546 gram. Fantastic. Okay. All right. Okay, so David, I get you. All right. Okay, so let's look at this together. Let's look at this together. Can you all see the slide? So who got the answer? This is the question here. Okay, fantastic. So you can all see the slide. Adebayo says yes, ma. So who got the answer? Where did you, oh, I almost got it, ma. Don't tell me no one won my recharge card in this class. So let's look at this together. What were the values given? Determine the quantity of carbon dioxide dissolved in 1 liter bottle of carbonated water if the pressure of 2.4 atmosphere is applied. 2.4 atmosphere is applied in the bottling process at 25 degrees Celsius. So how did you get, those of you who got 0.0806, I don't know why none of the 71.4 molar guys, I don't know why you didn't answer me. You probably would have won the prize. So those of you who got 0.0806, can one of you just quickly show me how you did it? Those of you who got C to be 0.0806 mole per dm cube, quickly, we don't have all the time. How did you work it out? Those of you that got 0. I know a couple of you said 71.4 mole per dm cube. No, 2.4. Why? Why are you? Let's go back. Let's go back. Oh, fantastic. Okay. So you see, I knew there was something wrong here. So fantastic, fantastic. Okay. So fantastic. Because what you have here is the Henry's loss constant of CO2 and not the pressure. So that's why you cannot say 2.4, which is the Henry's loss constant, divided by K. What you're looking for is the what? What are we looking for? The C. The C is equal to K times P, and the K is given. No, you don't have to cover your face. And the K is given as 29.76. So that is your K. You multiply your K by the pressure, and the pressure is 2.4. So I see where you got it wrong. I see where you got it wrong. Okay, so let's move on. Please that's why one of the things I asked when we, it's okay. All right, so that's why one of the things I asked when we started was, what's the unit of K? You need to be conversant of the units. Okay, so let's move on. So here you get your C, 71.42 mole per liter. So it means that in 1 liter bottle, the number of moles of CO2 is 71.42. And we all know that our number of moles is mass divided by molar mass. Mass divided by molar mass. For you to get the mass, you need to multiply it by the molar mass. If you did that, you're going to get 3,142.66 gram, which is 3.1 kilogram. Do we have any question from this example? Do you all understand the example? Type yes or no. Do you all understand the example? Okay. Okay. We're going to solve more examples probably in the next class. And then I think more exercise will also be posted on your LMS page for you to really grasp the calculation aspect of the Henry's law. So let's move on. Let's move on. All right, so Henry's law only works if the molecules are at equilibrium. Henry's law does not work for gases at high pressures because when you have gases at high pressure, you really don't have that equilibrium. And that is why your nitrogen gas at high pressure becomes very soluble and harmful when in the blood system. So your Henry's law does not work when your gases are at very high pressure. Henry's law also does not work if there is a chemical reaction between the solutes and solvents. So you have your HCl gas in water, for instance. When you have your HCl gas in water, what you have is dissociation of the HCl into H plus and Cl minus in solution, because HCl is a strong acid. So in this case, Henry's law is not followed, or Henry's law is not obeyed. Now, does this always fit? Like we said earlier, when you have very high pressure, Henry's law is not followed. So as concentrations and partial pressures increase, deviations from Henry's law become noticeable. This behavior is very similar to that of behavior of gases. Remember that ideal gases are found to deviate from the ideal gas law as pressures increase and temperatures decreases. So for this reason, solutions which are found to obey Henry's law are sometimes called dilute solutions. So when somebody is talking about dilute solutions, they are referring to those solutions that obey Henry's law. Now, Raoult's law and ideal mixture of liquids. Raoult's law and ideal mixture of liquids. Now, an ideal mixture is one which obeys Raoult's law. But let's look at the characteristics. Let's look at the characteristics of an ideal mixture before actually stating Raoult's law. So we're going into Raoult's law, but we want to look at the characteristic of an ideal mixture. Do we really have ideal mixture? Not exactly. There is actually no such thing as an ideal mixture. However, some liquid mixtures rarely get fairly enough to being ideal. These are mixtures of two very similar substances. When we say two very similar substances, it means that the intermolecular force of attraction between each of those molecules are almost the same with the other one in the mixture. So commonly quoted examples are hexane and heptane. So you have hexane, which is a 6-carbon chain organic compound, and heptane, which is a 7-carbon chain organic compound. We have benzene and methyl benzene. So you have a benzene ring, and then the other compound is a methyl substituent on the ring. So you have benzene and methyl benzene. We also have propan 1-ol and propan 2-ol. This mixture is very close to being ideal because they are almost similar. You have your hexane very similar to heptane. What you have that is different in that compound is just one extra carbon, that's CH2. So you have your hexane and heptane, benzene and methyl benzene, propan 1-ol and propan 2-ol. And like I was saying earlier, what makes them really look very similar is the intermolecular force of attraction between them. The intermolecular force of attraction between these two these quoted examples are very similar. Now let's look at how intermolecular forces work with ideal mixture. Now, for example, let's say we have um, a liquid. So we have liquid, this represented with this blue, the molecules are represented with these blue balls. So if in a pure liquid, some of the more energetic molecules have enough energy to overcome the intermolecular attractions. You know that for a liquid to turn to vapor, it needs to gain enough kinetic energy such that the intermolecular force of attraction will be broken. Once the intermolecular force of attraction between this molecule is broken, you have it escaping to form vapor. Now, there is the rate at which this liquid turns to vapor. It means there's a rate at which the intermolecular force between this liquid, between the molecules of this liquid can be broken, and you have the molecules escaping to form vapor. So in this particular example, we are assuming that about 4 of this molecule escape. This is an hypothetical example. So we are assuming that at a particular temperature, about 4 of these molecules escape. So at a particular temperature and time, about 4 of these blue molecules escape. So it means that at this particular temperature and time, the intermolecular forces between these ones that are escaping has been broken. Now, if you're saying that this liquid represented by blue molecules and this red balls that is representing another molecule, if you're saying that they are similar and the mixture of these two can form ideal mixture, it means that the intermolecular force of attraction between these red balls is the same as the intermolecular force between these blue balls. So it means the rate at which these blue balls will evaporate, or this blue liquid will evaporate, will be the same thing as the rate at which these red balls will evaporate. So look at these two examples. You have 4 molecules escaping, and then you have 4 molecules escaping from these red balls. They are both at the same condition. Now, if they are mixed, let's look at it when they are mixed. Now, when this goes into mixture, when you mix the two liquid together to form a mixture, what you have is 4 balls are escaping. But out of the 4 balls, we have 2 blue balls and 2 red balls. What this is trying to tell us is the rate at which they escape is still the same. It may seem as if we have 4 in one and then 4 in the other, but in this mixture, you have just 2, 2. When you say 2 plus 2, what does it give you? 4. And if you're saying that the intermolecular forces between the blue balls and the intermolecular force between the red balls are the same, so it means that the rate at which they will evaporate will be the same. So it means that at this temperature and time, 4 balls will escape. The same thing here, 4 balls must also escape, and they must be equal because both of them have the same intermolecular force of attraction between them. So it's going to take the same amount of time for them to evaporate. So that is what an ideal mixture is. An ideal mixture of two liquids must have the same intermolecular force of attraction, such that for you to break the intermolecular force of one, you need the same amount of energy to break the intermolecular force of the other. So let's read what we have on the slide. In a pure liquid, some of the more energetic molecules have energy enough to overcome the intermolecular attractions and escape from the surface to form a vapor. The smaller the intermolecular forces, the more molecules will be able to escape at any particular temperature. Now, if you have a second liquid, which is this red ones, the same thing is true. At any particular temperature, a certain proportion of the molecules will have enough energy to leave the surface. You might think that the diagram shows only half as many of each molecule escaping, but the proportion of each escaping is still the same. The diagram is for a 50-50 mixture of the two liquids. Okay, I think that's one thing I forgot to mention. The same amounts of the liquids are mixed, so you have them in the same proportion. That means that there are only half as many of each sort of molecule on the surface as in the pure liquids. Now, the pure liquids are when they are both separate. If the proportion of each escaping stays the same, so if the proportion of each escaping stays the same, obviously only half as many will escape in any given time. If the red molecules still have the same tendency to escape as before, that must mean that the intermolecular forces between two red molecules must be exactly the same as the intermolecular forces between a red and a blue molecule. If the forces were any different, the tendency to escape would change. So if the forces between them are different, then the tendency to escape will change. You would expect that the one that has okay, let me ask you. Let's assume that the intermolecular forces between the red and the blue ball is a bit different. Let's say that the intermolecular force between the blue is higher than the intermolecular force between the red balls. Which would you expect to escape more if they are in mixture? So let me rephrase my question again. Let's assume, this example we have given now, the intermolecular force is the same. So the intermolecular force between the red balls and the intermolecular force between the blue balls are the same. But let's assume now that the intermolecular force between the blue ball is higher than the intermolecular force between the red balls. And you now mix equal proportion of the red molecules and the blue molecules together, which would escape to vapor more readily in the mixture. The intermolecular force between the blue ball is higher than the intermolecular force between the red ball. The intermolecular force between the blue ball is higher than the intermolecular force between the red ball. So which would escape more? I wish I could take the percentile of the class, those saying blue and those saying red. The intermolecular force between the blue ball is higher than the intermolecular force between the red ball. Which would escape more? Remember that the tendency of escape is dependent on the force of attraction. If the force of attraction is higher, you are going to require higher kinetic energy before it escapes. I've even given the answer. So if the intermolecular force between the blue ball is higher than that of the red ball, you expect that the red ball, thank you, the red balls, Bukola, you are still saying blue. If the intermolecular force of the blue balls are higher than that of red, you're going to need higher force to break that intermolecular force off the blue ball. Oh, it's red. Okay, so now you get it. If you have a stronger force of, if you have a stronger force of attraction, it's going to require more energy to break that bond. Okay, so let's move on. Now, if the forces, I want this out of my face. Okay, anyway. If the forces were any different, the tendency to escape would change. Exactly the same thing is true of the forces between two blue molecules and the forces between a blue and a red. They must also be the same, otherwise the blue ones would have a different tendency to escape than before. So in other words, since they both have the same intermolecular force of attraction, it means that the red force of attraction is the same thing as blue force of attraction, and the same thing as what? Red blue force of attraction. And that is why you can mix them together and call them an ideal mixture. I think this is where we're going to draw the curtain for today's class. Okay, I think there's one more slide. If you follow the logic of this true, the intermolecular attractions between two red molecules, okay, we said it already. The intermolecular attractions between two red molecules, two blue molecules, or a red and a blue molecule must all be exactly the same if the mixture is to be ideal. This is why mixtures like hexane and heptane get close to ideal behavior. They are similarly sized molecules and so have similarly sized van der Waals attractions between them. However, they obviously aren't identical. And so, although they get close to being ideal, they aren't actually ideal. For the purposes of this topic, getting close to ideal is good enough. Thank you very much for your rapt attention. I want to take some questions before we end the class. Do you have any question, any observation, any contributions? It's all welcome now. Thank you too, Mercy. Okay, thank you, Tolu. Thank you, John. Thank you very much. Do you have any question, please? I want questions. Questions, please. Yes, we are. We're taking attendance. Oh, sure, you're going to get more questions to practice with. So just go to LMS page. We'll send you some questions, some practice questions for you, but please make sure you practice them. And also refer to the video. We're going to post this on YouTube. For some of you that could not join the live class, please go back to YouTube. Even for those of you, yes, the video, the link to this video will be available. Oh, yes. Okay, the link to this, let me take the questions quickly. The link to this video will be available on your LMS page, so you can always go to the video, you can download it, you can listen to it as many times as possible. So until you understand the concept, you're going to get the slide, you're going to get your notes on your LMS page. Michi, you're raising your hand. You can unmute yourself. Okay, I don't think you can. Michi is raising her hand. Okay, you can unmute yourself now. No, Michi. Michi.
I
Okay.
sorry, I wasn't along in the class because I came a little bit late because of network.
You
But
came what?
where I'm getting it mixed up is that this intramolecular attractions, on what basis are we going to make use of these intramolecular attractions? I don't understand it, like
Sorry.
intramolecular attraction between two red molecules and two green molecules, because I came a little bit late.
Okay. I didn't get that. I didn't get that very
Network is
well.
bad.
Yes, but I think what you asked is that when are you going to make use of the intermolecular force of attraction? We are about to go into Raoult's law. So in our next class, we'll be talking about Raoult's law. Basically, in this class, what we talk about majorly is Henry's law. We are moving into Raoult's law, but before we go into Raoult's law, we wanted to establish what ideal mixture is. So in order for us to explain what an ideal mixture is, we needed to explain what makes a mixture ideal. Now, in order for us to explain what makes a mixture of course, but really, like we said, okay, somebody is saying that, please, man, can an ideal mixture be composed of three substances? If that is possible, yes. If they are as close to one another as possible, yes. But the challenge is, like I said, we really do not have an ideal mixture. So, Michi, as I was saying, in order for us to explain what an ideal mixture is, we needed to explain the intermolecular force of attraction between molecules. Because for any reaction to take place, remember that anything in chemistry is reaction. If you are mixing two liquid, either you like it or not, you are carrying out a reaction. So for any reaction to occur, you are looking at the breaking and formation of bond. Now, for you to mix two liquids, it means that there must be some form of bond breaking and bond formation. So we are saying for an ideal mixture, the intermolecular forces between the liquids that are, or the solutions that are being mixed together, the intermolecular force of attraction between them must be exactly the same. So that's where the intermolecular force of attraction comes in. So don't worry, since you came a bit late into the class, you can refer to the video that will be uploaded shortly, and I'm sure you are going to get a hang on it. Any other question? Do we have any other question? Okay. In the absence of any question, I'm going to call it a day on this in today's class.